So if you look at this, what does it mean is this. When you have a cylinder or sphere, when the flow is incoming and make contact with the surface, in this point, of course, you have the so-called stagnation point. You still remember what is stagnation point? Yes. What is that? The velocity drop into zero. So here the pressure will be maximum. Right? Because you convert all the velocity into a static pressure or stagnation pressure. So here the pressure is maximum. And over here the pressure is minimum. Right? Minimum. So if the difference between this one and this one got bigger, you will have a bigger drag due to pressure. So you want to minimize it. How to minimize it? You need to minimize the wake region. The bigger the wake region, the bigger the pressure difference between front and rear part, and the bigger the drag. So you want to make it minimum. So how to make it minimum is by introducing a turbulator here. Why you want to introduce the turbulator? Because when you introduce the turbulator, this detachment will reattach to the surface of the this. So you will have a much smaller. You can see that for laminar, the flow separation occurs at 80 degrees, which means it is here, not even half of it. So over there, we will start to detach. Sorry. So the flow is coming, making a contact, which means it is attached to that. After 80 degrees, it is detached. So you want to make it turbulent such that it's attached here and it will keep attached until 140, only then it will detach. Right? So how to do that? One way is by introducing a strip. You can see here. This is a smooth sphere. This is a smooth sphere, right? When you have a smooth sphere, you can see the detachment start from here.
Yes.
Okay? But then, when you introduce a wire like this, then you can see it detached, but then it reattached again. So it is not fully attached, but it's reattached, right? Reattached and it detached in this region. Okay? So, for a smooth sphere, for laminar, the detachment will occur earlier as compared to when you have a turbulator installed in the sphere. And this is the von Karman vortex that I told you in the beginning. So this is the separation point, right? This is the wake from the bottom, and this is the wake from the top. Okay, if you know how to use Fluent, you can run it and you will have a good simulation on it. Okay, now coming back to here, the most important thing that I want you to know in this is the scale. Okay, you may see it's trivial, but you see the scale is not a normal scale. Okay, if you look at it, the scale is log scale. How to read this log scale? Do you know how to do that? Actually, I suppose not to tell you. Then I can do a trick with it. You see, this one is 10 to the power of 0. 1. So you see this one 1. This one is 10. Where is the 2? This line is 2. This line is 4. This line is 6, 8, 10. This one 20, 40, 60, 80, 100. 200,
600, 800, 1000.
Say 40,000. This one is 1,000. Okay, so you know how to read it, huh? Don't tell me later on that, oh, I got my Renault number 500. You just take in the middle like that. Right? If you do that, I have no hesitation to just scratch it. Okay? Okay, you know how to do it. Okay, now this is the reason why you have a dimple in your golf ball. Anyone play golf here? Okay. This one is the sport of executive, right? Boss. I cannot even afford to buy the stick. Maybe the ball also I cannot buy. Okay, so why do we need to put this dimple on the golf ball is because we want to make it turbulent. Right? We want to make it turbulent. Why? Because when we make a turbulent, you will have a thin wake. Okay? Thin wake region. The thinner the wake, the better the. Because then you will have a lower drag. Okay? However, okay, you want to make sure that the condition will be in this region. Okay. So if you guys ever seen the Mythbuster, okay, in one of those episodes, Adam and Jamie actually want to prove whether if you put the dimple in your car, it will give you a better fuel consumption, right? And the result is no. Why? Because this dimple has to be designed such that it gives you a low drag coefficient at the velocity where this golf ball is working. Right? When you hit the ball will be at certain velocity, right? So this dimple is only effective for those velocities. For different velocity, you have to get a different shape of dimple. You have to get a different shape of those things. Okay? So you cannot just arbitrarily implement it to your thing. Okay? So now you see this one. For a golf ball, you see the drag force or the drag coefficient will decrease when this Renault number is more than, this is 4, 6, 8, so around 6, right? 600,000, you can see that the drag force is lower. And luckily, the golf ball is usually hit at this velocity. Okay? Which means it is working on this range of velocity. Okay? If you are not a professional golfer and you cannot hit this velocity, what will happen is you will have a much higher resistance, a much higher drag. Okay? Like us, we are not professional. When we hit, we just, right? When you do that, maybe you will not hit the ball, but you will break your back. Okay? For us, we are not professional, right? We want to hit as much as possible. But remember, the ball is just this small. You put all of those momentum, those momentum will not be transferred to the ball. You will still have much more. And it will break your back, right? Because you have more. So it has to be just nice, right? So if you don't do that properly, your velocity of ball may be lesser than that, which means your Renault number will be lesser than this, ratio, which means you will not utilize the dimple of those golf balls.